Good afternoon, everyone. So I welcome you again to the second live session. So in this session also, we'll discuss about the application of MATLAB in solving optimization problem. So in the last class, we discussed an example to civil engineering, and I hope you'll be able to solve the problem using the MATLAB. So in that case, what we have done basically, so we have solved the problem using the MATLAB function fmincon. Okay. So the steps were discussed. So it was not that difficult. So what you have to do basically, that you have to define the design variable. So whatever variables you have for the particular problem you are considering, so design variable you have to define initially. Then you have to write the objective function and constraint function, and after that you can use the optimization function available in MATLAB. So in the last class, so we discussed the fmincon. Okay, so this particular function can handle a nonlinear optimization problem with nonlinear constraint, and you may have equality type constraint, inequality type constraint. So all types of constraint this particular function can handle. So therefore, so when you are defining, you have to define your objective function and the constraint, equality constraint, inequality constraint, and then if you have some linear your constraint, that also you can put within that function. And so that is basically you can solve a nonlinear optimization problem with equality constraint, inequality constraint, as well as linear constraint. Okay, so that we discussed in the last class. So in today's class, so we'll mainly discuss about some other algorithms. So there is another algorithm called fmin search. Okay, so this is basically this particular function you can use for solving unconstrained optimization problem. Suppose if you have only the objective function, you don't have constraint, so you in that case you can apply. But anyway, so once suppose within the constraint itself, so I have already discussed that if you have a constraint optimization problem, so that you can convert to an unconstrained problem using penalty parameter method. So if you do that, fmin search also can be applied for solving a constraint problem. But here, this is basically it is an unconstrained optimization solver. And then in today's class, so we'll discuss the least square nonlinear method. So that also will be discussed. And third one will be the genetic algorithm. Okay, so genetic algorithm also you can you can use MATLAB for solving a multi-object means it's a single objective today. So single objective optimization problem using ZA. And then if you have any questions, certainly you can write to us. So we'll try to answer those questions. So with this, I would like to invite Ms. Mahalakshmi from MathsWorks. So she will demonstrate, or she will basically take the tutorial that how you can apply the fmin source, then that nonlinear least square method, and then ZA. So over to Ms. Mahalakshmi. Yeah, please.
Thank you, sir. Thank you for the introduction.
Yeah, well.
I will share my screen. Can you see my screen?
Yes, it is visible. Yeah, you can go ahead.
Yes, sir. Thank you. Welcome to today's tutorial on exploring nonlinear optimization, comparing solvers on Rosenberg banana function. So I'm Mahalakshmi. I work as a senior online course developer at MathWorks. I have with me my colleague Shraddhara, who will be monitoring the chat during this session. So in today's session, we will solve an engineering optimization problem using Rosenberg banana function, a benchmark that mimics the narrow curved valleys often seen in real real world problems. So we will explore how different MATLAB solvers such as fmin search, fmin unconstrained UNC, and least square nonlinear, and the genetic algorithm perform on this function, and compare their results to identify the most suitable solver. By end of this tutorial, we will summarize the key learnings from solver performance and highlight how these insights apply to real-world engineering design challenges. And we will close the session with Q&A. And if you have any questions, feel free to post them in the chat during the session, and we will also revisit them in the final discussion. So now we will see how to solve the described engineering problem using MATLAB. So for this, we will use MATLAB online version. So all the registered learners for this NPTEL course have already have access to MATLAB online. So to access MATLAB online, so I'm requesting you all to go to the NPTEL course page of this course, optimization methods for civil engineering. So let me go to the course page. So I hope my screen is visible. So now you can go to the NPTEL course page and you can see the MATLAB in the course outline menu. So there you have three options. So the first one is MATLAB Access. So you click on MATLAB Access here, and this will give you three steps. So the first step is to create the MathWorks account. So if you have not created the MathWorks account, so you can create it through this link. Or if you have already created, then go to step 2, skip step 1. So in step 2, you have the link to access MATLAB for this particular NPTEL course. So you can click on this. So now this will lead to access MATLAB online page. So click on this button. Now click on Open MATLAB Online. So you will see MATLAB online page, which has mainly three sections. One is file section, other one is workspace, and the main section is live editor window. So now my colleague Shraddhara will share the work live script in the chat. So you all can download that live script and save it in your system. So once you have downloaded and saved in your local machine, now come to the MATLAB online. And in the file section, you can click anywhere, you can right click anywhere, and you can see the option called upload files. So you can click on upload files and you can open the file which you have downloaded in the system. So there is one more file which is called banana out, which is also needed to capture the iterations. So that is a .m file. So that also is shared in the chat. So you can download that file also and upload file in the MATLAB drive of the MATLAB online. So once you have downloaded, so there are two files. So one is the live script and other one is the banana out MATLAB script file. So now go to the file, whatever you have uploaded in the MATLAB drive. I have already uploaded. So search for the file and double click on this. So I'll make this in a bigger screen so that I'm double clicking on this live editor. So now you can see the full screen mode. So I hope everybody opened the live script. So now let's move to the tutorial. So when engineers design wind turbine blades, so not only wind turbine blades, so any structure, if they want to design, they face challenging trade-offs. So the blade needs to be efficient to extract maximum power from the wind, and it should be strong enough to withstand wind stresses, and also it should be lightweight to reduce loads on the tower. So designing such a blade involves balancing these requirements in a complex curved design space. So finding the optimal solution is like searching for a needle in a haystack. So you can see here the wind turbine, it has an airfoil structure. So engineers often face a challenge in designing this airfoil structure because the structure has to be made in such a way that it has to extract the maximum wind power. So this requires carefully managing trade-offs between structural strength, weight, and aerodynamic efficiency to achieve maximum performance. So without optimization, finding the ideal solution can be time consuming and the best design might be missed. So optimization helps effectively explore the design space and identify the right trade-offs and achieve solutions that balance performance, strength, and efficiencies. So if we want to write the objective function for this airfoil structure with respect to efficiency and stress, and you can see the objective function will contain sum of two squared terms. And if you visualize this objective function, and it looks like a banana curved function. So that means it has a valley kind of curvature so that many of the optimization solver will find very difficult to achieve the best solution. So to prepare for such real world problems where you have an objective function with very narrow and curved valley, then the engineers first test optimization algorithm on benchmark functions with similar landscapes. So one such example is Rosenberg's banana function. So this function mimics the problem what we have seen in the previous section. So banana function which mimics the same narrow curved valley structure. So by studying the solver behavior on this banana function, engineers can evaluate which methods are more efficient at navigating these tricky landscapes. So this knowledge then guides the choice of solver for actual engineering application, ensuring reliable and effective designs. So here we follow the series of steps to find out which solver is best suitable solver for this banana function. So as already we have discussed in live session 1, so the first and foremost thing in the optimization process is the defining the objective function. So the first step is the define the Rosenberg banana function, which is the test objective function. And second is we will choose the starting point. That is initial guess is also is a very important factor in optimization problem. And third one is we will run this optimization problem using different solvers. So we have chosen the 4 different solvers. So one is fmin search, and which doesn't which is derivative free solver, and other one is fmin unc. So this is actually estimating the derivatives and finding the optimization solution. And the third one is least square nonlinear solver. And fourth one is genetic algorithm. So we will run this optimization problem with these 4 solvers, and we will find the how many number of iterations are taken by each solver and how many number of functions evaluations happened to achieve the convergence and best solution. So we will collect all the solver outputs and we will compare, and we will compare the solver efficiency also. So these are the steps we are going to follow in this session. So now coming to the step one. So first we will define the banana function. So you can see the banana function or Rosenberg's function, how it looks like. So it has two variables. One is x1, other one is x2. And this is also having a sum of two square terms. One is x1 of x1 power 4 and x2 square. So you have the higher order design variables and also two squared of some terms. So this is very difficult for the solvers to get the best solution. So first we will define the banana function now. So in the line number 4, we have to define the banana function. So we will use the function handle here to define this. So we'll have the function handle. So function handle, we will use at x1, x2. So here two variables are there. So we'll use here f is equal to at x1 comma x2, then feed the objective function. So this at of x1, x2 will tell the MATLAB that we are going to feed a objective function with the variables x1 and x2. So once you have written the objective function or defined the objective function, now we will run this section. So the section can be run through this run section button, or you can have at the left side, you have blue dotted lines. So you can just click on the blue dotted lines using your cursor and you can see the section got run. And now you can see the output. So the output, if you want to see in line with the code, you can click here. So you can go to the right of the MATLAB online. You can see the vertical toolbar. So there you can see output inline. So, so since I have suppressed this, now again you can run, you can see the function. So once I have removed the semicolon, the function is appearing here. Now we will look at the banana function. So we will visualize the banana function in the 3D surface plot. So 3D surface plot requires the grid points. So for that you have to click you have to use mesh grid and the surface function. So how will we use mesh grid function? So in line number 6, you will be writing the mesh grid function, which provides the boundary for x1 and x2. So in line 6, you can write mesh grid and give the boundary for x1 and x2. So since it is a 3D surface plot, so x-axis is with respect to x1, y-axis is with respect to x2, and z will be the function value, which is calculated corresponding to x1 and x2. So in the mesh grid, you will pass two arguments. One is for x1, other one is for x2. So you will be splitting your design space from -2 to 2 with an equal distance of 0.05. Similarly, you will split your y-axis from -1 to 3 with an interval of 0.05. So once you have created the grid, next you can calculate the function value. So that is capital F, which is nothing but for each grid point, the function value will be calculated and it will be stored in F. And you will plot this surface plot using figure function. So we'll use figure, and now we will use surface plot, that is surf. So you can use surf of x1, comma x2 and the function. And if you want to plot the edges or grid points, you can plot, otherwise you can make it none. So now in the line number 10, we will use surf function. So surf of x1 comma x2 comma f. So x-axis is x1, x2 is y-axis, f is in z, and edge color is set to none. That means I'm not going to visualize the grid. Now we have formed a surface plot. So the banana function can be visualized through the 3D surface plot. And if you would like to know the contour plot of this surf plot, that means you want to have a 2D representation of this 3D surface plot, you can go for contour plot. So MATLAB has a function called contour. So for that, again, you will use figure and then you will use a function called contour. So in line number 17, you will use the MATLAB function contour and you have to give the boundary for it. So here f value will not be there. So you will use only x and y because it is a 2D plot. So contour of x1 comma x2 and f log space -1 comma 3 comma 20. So this -1 and 3 comma 20 is, you will have a 20 steps in between log of -1 and 3. So now you can visualize this plot you're using surf function as well as the contour. So you can run this section. Now you can see the surface plot of the banana function. So you can see it's a banana curved function. And if you would like to see the contour plot, you can see the contour plot here, which is a 2D representation of your 3D surface plot. So now we have visualized the banana function and we know what is the difficulty in optimizing this banana function. Let us move to the optimization solver. So first we will use fmin search optimization solver to optimize this curved function. So fmin search is a MATLAB solver. So that finds a minimum of a function with one or more variables. So it uses the Nördler-Met simplex method, which doesn't need derivatives or gradients. So this will not use any derivatives of the objective function. So this makes it useful for functions that are noisy, jumpy, or hard to differentiate. And it works best for small to medium problems without constraints, since it cannot handle limits on variables. And because it's a local solver, so the result can depend on the starting point and it might not find the global minimum. So MATLAB has a function like fmin search. So this solver will not use derivative of the function. So, and it uses the initial guess of -1.9 to 2. Now we will solve this banana function using this fmin search. So for that, you need to tell the MATLAB to use the options. Using that option, the fmin search will optimize the problem. So how do we set the options? So for setting the options, we will use optimset MATLAB function. So we will use the optimset MATLAB function here in line number 22. Optimset of output function at banana out and display comma off. So here these arguments, if you say output function banana out, so MATLAB calls this banana out function, so which you have already downloaded and saved in your file and which is also added in the MATLAB path. So this does, for each and every iteration, this banana out function will be called for plotting the best solution in the figure. Display off means this will not display any output information. So if you want to make this on, then you will see all the function evaluations and also you will see the iterations. Now we have set the options for the fmin search and we have given the starting point, that is initial guess for the fmin search to begin with. And this doesn't need the lower bound and upper bound. And in line number 24, using this options, we will use fmin search function and we will solve the optimization problem in using banana function. So now line number 24, you can copy this, whatever there in the chat, or you can do along with me. So fmin search of function. So here the function is banana function. It is defined here in this section. And x naught is the starting initial guess and options what we have already given. And this outputs the best solution value x and the function value and the exit flag. So exit flag is nothing but why the optimization problem stopped, whether the best solution is achieved or not, and the output. So this output contains all the information about the optimization solver. What is the how many number of function evaluations and what is the best solution and how many number of iterations. So all these are saved in the argument output. So now if you want to know only the functional evaluations, how many number of function evaluation. So why we need function evaluation? In order to understand the efficiency of the solver performance. So by seeing the solver performance efficiency, we can able to find whether the solver is efficient or not. So for that, we will extract the function evaluation from this output argument. So we will extract using function count. Line number 27, we will use f output dot function count. So output dot function count, which is saved in f count. Next, we will use display function to display how many number of function evaluations and how many number of iterations it is taking to converge the function. Now we will run this section alone. So when you run the section, you can see so you can see the banana function. Somehow now MATLAB Online is not supporting the graphics. Yeah, that's why the output is not seen here. But we can display the best solution here. So the best solution is 1 and 1. So x1 value is 1 and x2 is 1. And we can display the number of function evaluations. So the number of function evaluation for fmin search is 210 function evaluations. And number of solver iterations are 114. So the observation here, when we use fmin search, it didn't use the derivative of the function. So it took 210 function evaluations and it took 114 iterations to converge. So that is the observation here from fmin search. And next we will move to fmin UNC. So UNC stands for unconstrained. So here we have not used any constraint algorithm, but this fmin UNC uses the derivative of the function. So previously fmin search didn't use the derivative, and The function number of function evaluations are 210. Now let's see if we use fmin unc, which estimates the derivative of the function, and how many number of evaluations it is taking to converge. So for that, again, we will use the options and we'll use optim options. This is the MATLAB function we will use for fmin unc, and we'll use the solver fmin unc and the display of and output function. So this calls the banana out function for plotting the best solution and for calculating the derivative of the function which uses quasi-Newton method. And afterwards, we will use fmin unc, and this needs only three arguments. One is the function, which is the banana function, and x naught, and then options what we have specified. And the output of this fmin unc is nothing but x, fval, that is function value. X is the best solution, and this is exit flag and output. So output is having all the information about the optimization solver. So now we will run this function. I usually see the graphics here. Maybe I can go to the MATLAB desktop version and I can show you. Now we will compare the best solution. So the best solution what we got from fmin unc is 0.998, and for x2 we got 0.996, and the number of function evaluation it is reduced to 150, but for fmin search it is 210. And number of solver iterations for this, it is 34. For fmin search, it is 114. So now the number of iterations are very less, which is 34. So it converged faster. So because it found the derivative of each function. So that's why the solver has converged faster, and the solve iterations also only 34. And next we will go to the least square solver. So we'll use a least square solver because for this kind of functions, because banana function is having sum of two squared. Objective function have two squared sums. So now we'll use least square solver. We'll see whether this is giving a best solution and how many number of evaluation it takes. But one tricky here is the least square solver will not take the objective function directly using function handle. So we have to give it in terms of a vector residues. So here the residues root of the each term we have to say take. So each term root, that means 100, the root of this is 10, and here it is x2 minus x1 square is one residue, and the second residue is 1 minus x1. So we will use this residues of these functions, and then we will use least square solver for optimizing the problem. So here already the options are given the same as above. So we'll use optim options MATLAB solver, and the MATLAB function, the solver is LSQ non-lin. So this is the solver name what we use for least square optimization problem, and we will off the display. That means we don't want to see any progress in the command window, and we will call output function for output function banana out to see the each solution in each iterations. And now we will first define the residue because this least square function needs residues. So for that, in line number 39, we will use residues. So this is the residue, but the residues also can be uh, started with at of x. So at of x, 10x2 minus x1 square is the first residue, and 1 minus x1 is the second residue. So now we have defined the residues. Now we will run the optimization using LSQ non-lin. So now we will use the MATLAB solver LSQ nonlinear, and you will give, instead of direct objective function, you will give the V fun. That means the residue of the function. And we know the starting value, that is x naught, and lower bound on upper bound is not there. So it is 0 and options. So now let us run this. And here again, we use f count to know how many number of function evaluations. And we'll use output dot iterations to know how many iterations it's taking. So we usually get that graphic. So now due to some technical glitch in the MATLAB online, I'm unable to show that. At the end of the session, I can go to the desktop version of the MATLAB and show you. So now you can see through this least square optimization, the best solutions of x1 and x2, 1 and 1. So if you substitute 1 and 1 in the banana function, the minimum value of the banana function is 0. So that's why all the solvers have given the minimum value of 0 with x1 and x2 equal to 1. But only fmin UNC has given 0.9998. It used derivatives, but it has not given the minimum value. So here in the least square, it has given the best solution, that is 1 and 1, and the objective value function is equal to 0 at 1, 1. And number of function evaluation, it is just 87. So comparatively very lesser than other two solvers. And number of solver iterations is only 28. So now we can see out of these three solvers, now the best solver for this type of problem where the sum of squared terms are involved. For that, least square can be a best solution. And now let's move to the global optimization solver, which is GA. We'll see whether GA can able to solve this banana function very easily, or how many number of function evaluations or how many number of population search it is taking. So, but for your GA problem, you need to give lower bound and upper bound. So here the starting point, what we have given, initial guess, we have given as minus 1.9, minus 1.9 and 2. So lower bound and upper bound for GA problem also has been taken from minus 1.1 and 2. So here minus 2 to 2 is x1 boundary, minus 1 to 3 is x2 boundary. For this GA problem, we will use optimum option. Again, the optim options function we are using, and which solver we are using, that is GA, and the population size is 100, maximum generations 200, and function tolerance when it should stop 1 e power minus 6. So that is a stopping criterion, and we are displaying the number of iterations also, and we will use plot function. So this is the inbuilt function which will plot the best fitness values and also the average fitness value. And we will use the GA solver. So GA solver needs these many arguments. One is the function, that is objective function, what we have defined earlier, banana function, and number of variables. So here x1 and x2, both are two variables are there. So number of variables 2, and equality constraints and inequality constraints. Here we are solving unconstrained problem. So we don't have any equality constraints and inequality constraints. And we have only lower bound and upper bound. And we don't have non-linear constraints. So for that, this all are empty. And we will use options. As per the options what we have set, accordingly the GA will run the optimization problem. And after running, it outputs the best solution and the function values and the exit flag and also the output. Now we will display the GA algorithm results and what is the best solution and what is the function value and number of function evaluations and number of generations. Now I'll run this. So once you run this program, let me go to MATLAB desktop version. It's taking time. So this is the desktop version because as the MATLAB online takes time for me right now. So I have added all the codes from the beginning, whatever I've discussed. Objective function is defined. And for visualization, mesh grid and surf plot. Surf function is defined here and contour. So I'm just running section by section in order to understand. So contour plot. So here I have not downloaded the banana out function in desktop. So once this banana out function is called, this is what we have not seen in MATLAB online. So each time when the iteration starts, the best solution will be displayed here. Then finally it reaches the best solution point. So this is for fmin search. This is for fmin UNC, non-constrained. So whenever the function calls, MATLAB calls banana out, each time what is the best solution after each iteration will be plotted in a red color point. And optimization with least square. So we have seen it is a best for these kind of banana function because it has only 87 function evaluations, 87 function evaluation, and the solver iterations are only 28. And we were seeing GA algorithm. So when we run GA algorithm for this kind of optimization problem, you can see the best fitness and the mean fitness here. So whenever it searches, the best fitness value is plotted in red color dot. I'll minimize this window. Now you can see here we have made display iteration. So all the iterations are displayed. Otherwise, you can make it off. So you can see the best solution is 0.99921 and x2 0.99842 using GA algorithm. And the function value is also displayed here. And number of function evaluations, it is 13,120 because this doesn't use the guess value, starting initial guess value, but it uses the bound. Within the bound, it searches entire space. So for these kind of problems, it is taking number of evaluations or function evaluations of 13,120. So if we discuss the results, you can see the fmin search used 210 function evaluations and number of iterations are 114. And fmin UNC, it used estimated derivatives of the function. So number of evaluations are reduced and number of iterations are 34, but it couldn't give the best solution. And least square nonlinear function solver, it has used the sum of least squares. So number of function evaluations are 87 and number of iterations are 28. And for GA, the number of function evaluations are very high and the number of generations are 108. So if you run just GA again another time, it won't give a same answer. So it might be a different answer. So we will not get a best solution in every time. So the best solution might vary each time when you run. It is actually searching for the globe entire space. So the best solution is not constant here. So next time when I run, I will be getting a different solutions. So now you might have got a question like why GA is not suitable, for which function it will be suitable. So for that, if you take the function which is having jumpy functions, or if there is any discontinuity in the functions, or if the function is oscillating. So we know that the sine function is the oscillating function. So for these kind of oscillating function, we can see whether the genetic algorithm is really holding good or not. So we can compare that genetic algorithm with the very well-known optimization solver, that is fmincon. So now if I run this, you can see the function is like a oscillating function, but using fmincon, we could find the local minimum at this point. But the actual local minimum is this point. So the GA can find the exact global minimum of the function, but your fmincon cannot able to find the function best solution for the function because it is a oscillating function. So there are some advantages and disadvantages of using classical solvers, and the same applies to global optimization solvers also. So GA can be well suited for any discontinuous or oscillating functions. So now that we have concluded um, which solver is best suited for which kind of function. So for that we have taken a banana function, and also we have taken a sine function. So for the banana function, which has a squared terms. So for that, the best solver is a least square solver. But for global optimization solver can be used in case of the oscillating functions or any discontinuous function. So this is the conclusion from this tutorial. So if you have any clarifications or any doubt, you can ask or you can write to us. So I'll stop
Yeah,
sharing.
thank you. Yeah, thank you. Uh, yeah, so I'd like to just add a few points here, I think, which has already been touched upon by Ms. Mahalakshmi. So basically, I have also said this thing during my lecture video also, in my lecture video also. You just see now, you have, suppose today she has considered mainly the admin, that is unconstrained one, then admin source, okay, which is not using the and then genetic algorithm. So what I said in my class also, that if your problem or if your function is a continuous function, okay, so don't apply any sophisticated algorithm like genetic algorithm, or any non-classical algorithm is not required, okay. So you can solve your problem easily using the classical method. So at that time, so you have seen basically that when you are applying GA, so it is taking lot of iteration, lot of function values, okay, function evaluation. That is very expensive, and I think you should recall that in my first class, when I have, or initial classes, when I have discussed the algorithms like golden section search method, then interval halving method. Okay, so how I have compared the efficiency of different algorithms. So efficiency of different algorithms were compared in terms of function evaluation. So if your number of function evaluation is less, so in that case you can tell that your basically algorithm is efficient. Suppose when we are discussing interval lapping method with golden section search method, okay, so golden section search method is taking lesser function evaluation than interval lapping method. So basically, so you can conclude that okay, it is a better algorithm than the other one. Similarly, here also you can compare in terms of function evaluation, that if your number of function evaluation is less, so you can say that okay, this algorithm is your efficient, the other one. Now, in comparison to genetic algorithm, certainly the other algorithms are better. But as I said, that there is no free lunch. Okay, there are some problem like the discontinuous function. Okay, and you have multiple optimal solutions. So there are function, and when you are handling your problem in real means of real life problem, so you will see that that the function may not be differentiable, okay, it's not continuous. So in that case the gradient based algorithm will not work, okay. So in that case, what you have to do basically, in order to find out the global optimal solution of the problem, you need to apply the algorithms like genetic algorithm, differential evaluation, particle sum optimization. Okay, so these are some of the algorithms so that you can apply. So I think we can conclude with this, that if your problem is simple one. Okay, so is continuous function. Then you just apply the classical method, and with a very few iteration, you will get your solution. Okay, so with this, if you have any questions, so certainly you can write to us, and that we'll try to address in the next live session, or basically we'll try to in the dashboard itself. So we'll answer those queries. So thank you very much. So I would like to conclude today's live session. Thank you so much. Thank you to all.
Um, Yeah, sir, actually, we would like to give some like assignments based on this live script.
Yeah,
So,
yeah,
in the course page, there is a
yeah,
MATLAB, under MATLAB, assignment
yeah,
related sources are there. So,
yeah,
I'll just show them how to download
yeah.
and use it. Thank
Okay,
you.
okay, please.
Thank you. In the NPTEL course page, so under MATLAB, you can find downloadable resources and references. So there you can find the MATLAB link. So when you click the MATLAB link, so you can find 4 assignments. So you can download them. And as we have discussed in the well starting, you can download. Then you can go to MATLAB online version. So it will be a zip file. So you can unzip it and you will find 4 assignment questions, and you can download them in your local system. Then go to MATLAB online using the access link and go to the file section. So you can just click here, the file section. If the file section is not visible, you can go to the left vertical bar and click here. You can see the file section. If the command window is not visible, you can click here in the horizontal toolbar. So right now the command window is not needed. So then the assignment questions can be uploaded. So this is your file section, and you can click here and upload files. So now, right now it's there in my downloads. So you can upload directly the zip file and you can unzip. So when you click, you will double click on it. You can open the assignment V1. So as per the question, you can run the section. This is run. Here you will find the run button, green color arrow button. So you can run and get the answers or solution for this program. So if you are unable to see the output, you can go to the right side vertical bar, pause your mouse for some time. So there you can make it output inline. So when you make it output inline, you can see the solution then and there inline with the code. So your assignment 12 will be based on the live scripts. So you can use the run section to run the live script. Yeah, so thank you for listening.
Yeah. Okay, then.
Thank you.
Yeah. Thank you.
Thank you.
Thank you so much. Yeah, we can conclude. Yeah.
Thank you. Thank you.